Hello and welcome back to App for You. In this particular video, we'll be discussing a new problem, basically from Traversal. So we have basically started the Traversal playlist on trees. Basically, we have started the tree playlist, and we had discussed a problem from pre-order Traversal. We discussed two approaches, a recursive approach and a non-recursive approach. So I discussed everything in detail, how we solve the particular problem recursively and non-recursively. Two videos are already uploaded, please visit them. So in this particular video, we'll be discussing what basically is an in-order traversal and how it is solved using recursion, and basically we'll focus on the non-recursive approach in this particular video, right? I'll just give you the pseudocode of the recursive approach, but we will discuss and implement the non-recursive approach in this video. So first of all, let us understand what is an in-order traversal. So basically we had already been familiar with the pre-order traversal, where the word pre indicates that the root node will be visited first, printed first, and then we go for the left and then with the right. So this was basically the pre-order traversal. So pre here indicates the position of the root. Now what happens in the in-order traversal? In the in-order traversal, basically what happens, the root will be processed second, right, and left will be processed first, and the right will be at the end. You can see the position of root is in the middle, so it is an in-order traversal, right? Whereas in the pre-order traversal, the position of root is in the beginning, and then left, then right. But if the root is in the middle, then it will be in-order traversal. So we discussed the pre-order traversal, and it was solved recursively by, first of all, when we are getting the root node, then we were printing the value of the root node, then we were passing the pointer to its left child and the pointer to its right child to the pre-order function. So means there were two recursive calls, one recursive call on the left child and one recursive call on the right child, right? So what was the process? First of all, print the current root's data, then a recursive call on the for the left child and a recursive call by passing the right child pointer. What happens in order? So if you just focus on pre-order and in order, compare them, you'll just find the only difference is swapping of these two lines. What happens in order is basically we also receive a root here, root address here, the address to the root node, and what we basically do is basically first of all we perform the in order on the left child, right? And once the in order traversal of the left subtree is completed, then we will print the value of the root node. You see root node's value is printed in the between, and once this is printed, then we basically do the recursive call on the right child's node. Basically it means that if you look into the pre-order traversal, so pre-order traversal, what was happening, we were having this as the root. So this, on receiving this, what we used to do basically, we used to print 1, and once we printed 1, then we used to do a recursive call on this left subtree, then it returned, and then finally we did a recursive call on the right subtree. So this was pre-order. What happens in order? In order basically we are at 1, but we will not process 1 right now. What we will do instead, we will just go front to the left subtree. We will process this left subtree. On returning, once I return, now I will print 1, and once 1 is printed, now you will process the right subtree. So this can be clearly observed from the algorithm that is given here, the pseudocode of the in order. So clearly they have mentioned that first of all we do in order root left, means a recursive call on the for pre-order traversal of the left subtree, in order traversal of the left subtree. Once this is completed, you come back, now you process this particular node, so root data, and now then you just go for the in order traversal or the right subtree, right? So this was the approach that we basically followed, right, in the pre-order, and just by making this change you can successfully convert this problem into the in order traversal, right? Now comes the point about the non-recursive approach. So we have already discussed about the non-recursive approach of the pre-order traversal, right? So basically the idea of the non-recursive approach in the pre-order traversal was that we have to simulate the problem by using a stack, right? So basically we were using a stack, so use of stack, and what was the logic? Logic was, suppose in pre-order what we used to do, if you just focus on the pre-order traversal, what we used to do. So basically I have the slide here, let me take you to that slide. So pre-order non-recursive approach, yes. So if you just focus on the pre-order non-recursive approach, they had strictly mentioned the algorithm to simulate. What we used to do, first we process the current node. The current node was processed first. Once this node was processed, then we used to call the left subtree, right, the in order traversal of the left subtree. But before moving to the in order traversal of the left subtree, what we used to do, we used to store this address in the stack, right? Before going to the left subtree, we store the current node on the stack. So address of 1 was stored into the stack, and once you store the address into the stack, now you are free to do the in order traversal of this particular node, right? After this particular element is completely processed, right? This left subtree has done its job, right? What we used to do, pop the element and go to its right subtree, right? Then we used to go to the right subtree, right? So we will continue this approach until the stack is non-empty. So we already have made the video on pre-order traversal for non-recursive approach. So please this is must watch video, right? You must watch it because I have explained it in detail how actually this particular algorithm is working. Having said that, we just got an idea that we are actually going to use the stack, right? So how we are going to use stack? Basically, as I said, since this is pre-order, so first of all you will process this node. Now you want to move to the left subtree, but before moving to the left subtree, you have to store this address into the stack. We will push the address of this into the stack, right? And once we push the address into the stack, now we can just pick up this node and repeat the process, right? Then again they will pick up this node. This will be repeated. This is already explained in the video. Now once all the nodes are processed in the left side, then what we will do, we will start popping the element from the stack if it is non-empty, right? We will pop the element and then visit the right subtree of that particular node, right? So this process will continue until the stack is non-empty. So to make it more clear, let me do one thing. Let me show you the code first of all about what was actually happening in that particular case. So if I show the code, so let me just open the code for the pre-order traversal that I had explained in that particular video. So if you look at the code for the pre-order traversal, then you can see what we used to do. Basically we used a stack, so we were declaring a stack, right? The moment we declared a stack, then we used to enter a while loop, right? This will continue until it is breaking at this point, and we got a node while root not equal to null, right? And then we used to do what? Stack. See, this is pre-order traversal, okay? Pre-order. So as per the pre-order algorithm, what we used to do, first of all, we used to process the root node first. So root node is processed here, root processing. Then the left subtree, the traversal of the left subtree, right? This will continue. Now if stack is empty, we used to break, but if it is not empty, we used to pop and then do the right traversal here, isn't it? The right traversal was done in this side. So this particular explanation is already available in that particular previous video. In this video, I will focus on converting this particular problem to in order problem, right? So that is why I am saying the prerequisite is please watch the video to pre-order traversal for complete understanding. Then you can jump to the in order traversal. So now what am I going to do? In the same code, I will just do slight changes. Slight changes in the sense, here what we are doing, here in pre-order traversal, first of all we are doing the processing of the root node, then I am doing root equal to root left, right? And then finally if it is empty, I will break, otherwise I will pop an element and then move to the right subtree. There will be slight change. What will be the slight change? Instead of pushing the root node first, what will I do? I will perform the root equal to root left first, right? Because in order says left, root and right, right? So but first of all I will process the left side, then I will just move to the root, and then finally I will do the root equals to root right. Getting the point? Means these lines will be interchanged. One goes up, one goes down. Means I will not push earlier. First of all I will allow the function to perform this root left, because left should be processed first. Then I will perform root here, that is perform the processing of the root node. Then finally I will perform the processing on the right node. Let us see the code for this. So I will now write the code for this particular problem. So as I said, this particular function here, what will I do? First of all, I will be declaring a function here that will be solve, right? So as we generally do, we will declare function solve here, and solve will get the root node. Fine. So this particular function solve will get the root node. So I need to declare a function here which will be void solve, right? So basically let me write void solve. Void solve. Fine. What will it receive? It will receive the address of the root node. Fine. The explanation is already available in the previous videos why I do this, why I create a function called void solve. The in order traversal I will perform in this particular function, okay? Solve function. Now talking about the, they have now in this particular problem, if you go to the problem statement, they have mentioned here that we have to basically return a list containing the in order traversal of the tree. So basically you have to store the in order traversal into a list. For that particular reason, I will be basically declaring here a vector which will be of integer type, right? So sorry, not vector. Let us give it a name output, which we generally do. Fine. So vector integer output. So this is the name of the vector that I created. Now what happens in the solve is basically here I will create a stack because I'm going to use a stack for my in order traversal iterative approach. So I'll say stack. Now what type of stack, what type of values will it store? It is going to store the address of node. So type will be stack node star and stack. Fine. What is the next approach? We know we are going to run a continuous loop while one. Inside it I will check if the root node is valid while root not equal to null. So basically if the root is not equal to null means we are fine. What can I do? Now since we are performing in order traversal, so in order traversal basically says first of all process the left, then come to the root, then right. So since I am right now pointing to the root node, right? I am right now pointing to the root node. Initially I am pointing to the root node. Let me draw the diagram. Suppose 1, 2, 3, 4, 5, 6 and 7, right? So initially I am pointing to the root node, but I don't want this to get processed right now. What will I do? I will store its address into the stack because I will be coming back, right? So for that what I am going to do is basically stack dot push root. What will it do? It will basically push the address of this particular node into the stack. What's next? Now I'll move left, isn't it? Now I'll move this particular pointer, root pointer to left. So this will now point here, not here, here, okay, in 2. So what will happen now? For that I will do root equal to root left. Fine. What next? Now since it is already pointing to root equal to root left, now one more thing. Once this gets processed, okay, now when should it stop? It should now move to 4, and now it should stop when it will get null. 4 left will be null. It should stop here. Now when it stops here, what should I do basically? Now while I was traveling from 1 to 4, you see I am just pushing the elements into the stacks. Means I have a stack. Initially I pushed 1, then I pushed 2, then I pushed 4, right? Right now 4 is pushed into the stack and I am on left, and this is equal to null, so it will not enter the while loop. What will it do then? It will check if the stack is empty. So if stack dot empty, what does it mean? It means that we have no more nodes left to traverse, so basically we will break, right? We have already discussed this in the previous video. Otherwise what will I do? Otherwise we should basically point the root node to stack dot top, means the value at the top of the stack, that particular address, we should point root to that particular address, and finally remove the top element of the stack. Why didn't I just write stack.pop here? Because stack.pop here does not returns anything, okay? It will just remove the top element from the stack, but I want the address to get returned. So for that you should write root equal to stack.top, and then you just remove and then you can perform the pop operation, right? This is a good way to do it. Fine. What next? So now what does it mean? That it means that now since my pointer was right now here and this is null, so what will I do? I will say pop the topmost element from the stack. So 4 is popped, so pointer comes to 4. Now what should we do? We should basically process the we should now process this particular element, right? Because it is in order. Left subtree is already processed. When we return to root, we should basically process the root. So for that particular point, what should I do? Just after the element is received, I should, instead of writing cout root data, we should basically insert that particular data into output vector, right? The vector that we created, output dot push back, right? Output dot push back what should we push? Root data, right? And once you pushed it, that's fine. Now you can go point your root to the right side, root equal to root right. Yeah, so that's a good way to do it, and I think this should work because see, we have already done the approach. Now it will point to the right side. Now it will point to the right side in the sense it will point to this. Again it will be null in the sense what will happen? This element is already popped, null, so stack not empty, so it will pop another element from the stack. 2 will be popped, and now pointer will point to 2. Now pointer will point to 2, so basically it will perform this push operation. So basically initially first time 4 was pushed into the output stack, next time 2 will be pushed into the output stack. I hope you are understanding what I am going to do here. Next again after 2, root equal to root right, so basically it will point to 5. So 5 is also not null, so stack dot push root 5, so 5 will be pushed here, and you know that root equal to root left, right? So basically left is also null, right is also null, so you can just return it. Getting the point? So if I talk about the traversal of this particular output, let us just try and do it, right, for making it more clear. The code is already running, so first of all let us run the code for clarification. Alright, I think I forgot something here. See, this is solve root, right? But you have to return something. What should be returned? Return output, right? And before that you should write output dot clear, as we used to do in the previous problem also. So the problem is working fine, and I hope this should give the correct answer. That's it. Great. So the code is actually working. Now let me show you the why actually the code is working fine. So I'll be very quick here. Let me just increase the size of the screen. Alright, fine. So you see, we have, I'll take a small tree, okay, 1, 2, 3 and only 4. That should do actually. 4 and 5 suppose. I'll take 6, 7, no problem. 5, 4, 5, okay. So what is the problem? Initially I have root here, right? So root is not equal to null, stack dot push root. So I will have a stack, I'll push root. What is root? 1 is pushed here, okay? Address of 1 is pushed. Root equal to root left. Now root will basically point to this particular point. This is also not null, so what will it do? Stack dot push root. So address of 2 is also pushed. Now it will come here, not null, true. Stack dot push root. So address of 4 is also pushed. Fine. Root equal to root left. Now if it points here, it is null basically, right? So when it is null, it will not go inside the loop. Basically it comes out and check if stack is empty. So obviously stack is not empty. What will I do? Root equal to stack dot top. Stack dot top is A4. So basically this will be picked up. Okay. Means the pointer now root will basically point to the A4. Now root will point to A4. And then what do we do? Output dot push back root data. So this is the output array. 4 is pushed here. Fine. What next? Root equal to root right. So right now root is at 4. So 4's right is nothing but null. So now root will point to null. And if it is null, it will not enter here, and instead it will check if stack is empty, right? So stack is empty, false. So root equal to stack top. Again we will pick up the top element. So top element is A2. So A2. So root will now point to A2. Got the point? Now output dot push back root data. So 2 will be printed here. Root equal to root right. What is root right? Root right now is pointing to 2, and its right is 5. So root now points to this. Okay. Again 5 is not null. Stack dot push root. So what will be pushed? 5 will be pushed, right? So we have 5 here, right? A is already inside. Address of 1 is already inside. Address of 5 is pushed now. Now what happens? Stack dot 5 is pushed. Okay, fine. I was here, right? Root equal to root left. So left of 5 is again null. So if it is null, it will check if stack is empty. If stack is not empty, again I'll pop the top element. 5 is popped out, and I'll print here 5, right? Because after popping, what do we do is basically print the root's data. So root was 5, right? So now root equal to root right. So root right means right of 5 is again null. Null in the sense you come back here. Root not equal to null, false. Come here. Root is empty, false. Stack root equal to stack dot top. So top is A1. So now root will point to A1. Fine. Once root is pointing to A1, let me make these things more clear. So now our pointer root is basically pointing to A1. So what will we do? 1 is not equal to null, true. Stack dot push root. So you see, stack dot I did this one, right? Root equal to stack dot pop will basically pop out 1. Yeah, so it will pop out 1. 1 is popped out, and output dot push back root data. So 1's data means 1 will be basically written here. What the point? That is fine. So what next? So next time what will happen is basically, we know that next time after this particular operation, means after the output is pushed here, 1 is pushed here, root equal to root right. What is the right of 1? Right of 1 is 3. So 3 will be not equal to null. It comes inside stack dot push root. So address of 3 will be pushed. Root equal to root left. Root left is nothing but 5. Fine. So root is now pointing here. What happens? It is null, and if it is null and stack is non-empty, basically it will say point root to back to the top element. Top element is A3. So root will now point back to 3. Not 1, 3. Root is pointing back to 3. Now if root is pointing back to 3, what is the next step? Next step is, this is already popped, right? Next is output dot push back root data. So root data is basically 3, so push 3, right? And root equal to root right. Again, root right is nothing but 5, null, because root is right now here, root right will be here, so root is pointing now this side, which is null. If root is null, we know they will check if the stack is empty. So obviously stack is empty now, so it will break. What is the in order traversal? 4 2 5 1 3. You can see like this also. We can just say 4 2 5 1 and 3 is the correct answer, right? 4 2 5 1 3 is the correct in order traversal. Fine. So the video is getting lengthy. I should stop here right now. So basically, that's all from my side. I hope the video was quite helpful and intuitive. This is how we can solve this particular problem in non-recursive approach, okay, means iteratively. So this was an in-order problem. I was quite fast in this video, but if you want more clarification, you can visit my previous video on pre-order traversal. I have explained them in detail, and so I said that the prerequisite was the previous video. So that's from my side. I hope this video was helpful. Please put your doubt, if any, in the comment section, and like, share and subscribe. Thank you.